Welcome back to the video course on fluid mechanics. So, in the last lecture we were discussing about the kinematics of fluid flow. So, in kinematics of fluid flow, as we discussed, we are studying fluid mechanics without much consideration to the forces upon which the fluid flow is governed. So, without the effect of the without much concern to the forces, we are trying to say derive various equations and various theories as far as fluid flow is concerned. So, we have already seen the say the velocity field, then the acceleration field, and also we have seen the how the flow can be expressed in 1 dimension, 2 dimensions or 3 dimensions, or flow can be in steady state or unsteady state. All these aspects we have seen in the previous lecture. Also, we have seen that the fluid flow can be described in terms of either Lagrangian description or Eulerian description. So, in the Lagrangian description, we are just tracking certain particles, fluid particles, and seeing with respect to time what happens to those fluid particles. But in say Eulerian approach, what we are doing is we are say taking a particular point or particular section of the fluid flow, and then we are with respect to space and time, we are just checking what is happening to the fluid particles passing through that particular point or section. So, we are generally in fluid flow problems, we are generally using Eulerian approach, since it is much easier and we are much interested what happens to say the fluid flow at particular section or particular point. So, and also we have seen that as far as the fluid flow is concerned, we can describe with respect to say the acceleration is concerned, we can have a local acceleration and also we can have convective acceleration. So, total acceleration is with respect to the local acceleration and convective acceleration, and with respect to this we have also discussed about some numerical examples. And we have also seen say with respect to the when we discuss the fluid flow parameters, we will be describing the time rate of change for given particles, say with respect to local and with respect to convective and convective cases as shown in this slide, and this is called as the material derivative. So, these things we have discussed in the last lecture. So, now say we will see we have seen that the fluid flow can be described in 3 dimension with respect to x, y and z coordinates and with respect to time. But say it is many times it will be very convenient if we can describe a fluid flow with respect to the streamline, since streamline, as we have seen earlier, streamline is a continuous line drawn that is tangential to the velocity vector at every point, that is known as streamline. So, since the flow is with respect to its direction only, we are describing the streamline. So, say it is always advantageous if we can describe the fluid flow with respect to the streamline coordinate system. So, if a velocity vector is defined as v is equal to the unit vector I into u plus unit vector j into v plus unit vector k into w in 3 dimensions, then say the differential equation for streamline we can define as dx by u is equal to dy by v is equal to dz by w. So, this is as far as the 3 dimension flow in x, y, z direction, the velocity components u, v and w are concerned. So, the differential equation for streamline is generally described as dx by u is equal to dy by v, that is equal to dz by w. So, the streamline is a continuous line drawn that is tangential to the velocity vector at every point. So, this will be very useful if we can say most of the fluid flow, if we can describe in terms of the with respect to streamline coordinates, it will be very advantageous in many of the fluid flow problems. So, here in the slides, so the streamline coordinates with respect to streamline coordinates, the flow is described. So, streamline coordinates, it is a coordinate system defined in terms of the streamlines of the flow. So, here in this slide you can see that say this is the streamline streamlines are drawn with respect to x and y axis in 2 dimension. So here the streamlines are, say this shows, say with respect to flow, these streamlines are shown here with respect to n is equal to n1, n2, like that. So and then its normal direction with respect to that is shown as s1, s2, like that. So you can see just this is just like a flow net where the streamlines and then its normal lines, which is the equipotential line generally. So this is a flow net. So instead of describing the fluid flow with respect to this xy coordinate system, here we can describe the fluid flow with respect to this, say S and N, so that say the streamline and then it's normal, so that it will be, say it is in the direction of the fluid flow itself. So that will be much advantageous as shown in here. So the flow is described with respect to the streamline coordinates. So this has got the advantage that, say as far as fluid flow is concerned, streamlines gives the natural coordinate system. So that is one of the most advantage, the one of the advantage of the important advantage of this streamline coordinate system, since a natural coordinate system itself is flow, so that its direction itself is taken as the coordinate system, so that we can describe many of the fluid flow properties with respect to this coordinate system. And flow is described as one coordinate along the streamline S, and then second coordinate normal to the streamlines N. So as described, say that there is a normal lines and then a streamline. So S here is the say in the previous figure. So S this indicates the streamline, and then these normal lines are also drawn. So with respect to this, say the flow is described with respect to along the streamline S, and the second coordinate is normal to the streamline N. So flow plane is orthogonal curved net of lines, say instead of this the Cartesian coordinate system which we generally describe. So here the flow plane is orthogonal to the curved net of lines, and the advantage is that velocity is always tangent to the S direction or the streamline direction, so that we can write we can describe the velocity vector as v bar is equal to v into s bar, which is the streamline coordinate system. So say many times we will be describing the flow system with respect to the streamline coordinates, since it has got its own advantages compared to the other coordinate system which we generally use in mechanics. And then the acceleration is described as dv bar by dt. So that is here as into s bar plus an into n bar. So where as and an are the acceleration components in the direction of streamline and its normal direction, so that the acceleration is described as as s bar plus an n bar. So this streamline coordinate system is most of the time we use, since it has got its own advantage in fluid flow description. Okay, now before describing, say before going to the some of the fundamental theories and principles with respect to the fluid kinematics, so we will discuss the control volume and system representations. So this we have seen earlier, but still since we are going to derive various equations now. So before that we will further discuss what is a control volume and what is a system representation. So a system is a collection of matter of fixed identity. So if you consider, say for example here, say in this ball, so here inside, what is inside, whether it is fluid, it is either it is water or gas, water inside in this ball. So this is a fixed, it has got its own fixed identity, and it is a collection of matter inside fixed boundaries. So for example, as say the mass of air drawn into an air compressor, or the inside the air in this ball. So all this consists a system. So a system approach is very much used in fluid mechanics, since most of the time we will be interested to see what happens to the fluid inside a system. And then a control volume is, as we have discussed earlier, control volume is very used in fluid mechanics. So control volume is the volume in space through which the fluid flows. So for example, if you consider a small pipe like this here, so here when the fluid is flowing from one direction to another, so the control volume, say if you consider between one section to another section, so in between that space through which the fluid flow, that is the control volume which we are considering as far as the derivation of various fluid flow theories are concerned. And also sometimes we can have deforming or control volume. So here you can see that this is just like a balloon, so it can deform, so that at say one time there is a very less fluid or gas is inside, and then say if you blow it up, then you can see that it is full, so that this is deforming. So this is called just like in a balloon, it is called say a deforming control volume. So it is either a deflating balloon or just like a deflating say plastic material as shown in here. So this shows the deforming control volume. So many times instead of a fixed control volume, we can also use deforming control volume as far as the fluid flow theories or the development of the equations depending upon the problem. So now before going to the derivation of the say continuity equation based upon the consideration of mass and other equations, we will discuss one theorem called Reynolds transport theorem. So this Reynolds transport theorem is one of the fundamental principles used in fluid mechanics, based upon which many of the fundamental theories or fundamental principles are derived. So according to the Reynolds transport theorem, this laws according to this laws governing fluid motion using both system concepts and control volume concepts. So we have seen the case of say system concept and control volume concept. So most of the time this Reynolds transport theorem is the law which governs the fluid motion in either a system concept or control volume concept. So to do this, we need an analytical tool to shift from one representation to the other. That means when we are describing the fluid flow from a system approach to the control volume approach, or the from control volume to a system, so we need a analytical tool which can easily use so that we can shift from one representation to the other. So this Reynolds transport theorem provides this tool. So Reynolds transport theorem is generally used say, as we have seen, most of the time we will be using either a control volume approach or a system approach. So when we want to shift from one approach to one representation to another representation, we can use this Reynolds transport theorem, which is described here. So according to the Reynolds transport theorem, it gives the relationship between the time rate of change of an extensive property for a system and that for a control volume. So we can describe a fluid flow with respect to a system or a control volume. So for example, take any properties like velocity, pressure, or any of the other properties of fluid flow, then Reynolds transport theorem gives a relationship between the time rate of, as written in this slide, it gives the time rate of change of an extensive property for a system and that for the control volume. So if there is a system inside on which we are dealing, and then when we are considering control volume between in that, so how the with respect to time, how a property is changing, so that is what the Reynolds transport theorem describes. So here you can see a control volume here. So here the on this section the velocity is v1, and at the second section here the velocity is v2, and here say delta 1 is v1 into delta t, that means the fluid movement with respect to time, delta 1 is v1 into delta t, and here v2 is equal to delta 2 is equal to v2 into delta t. So then with respect to the changes taking place, say here is the control volume of the fluid. Initially it is like this, and after delta t, so it is shifting to the control volume is shifting like this in this slide. So delta changes after T plus delta T. So, if the delta is the control volume which we are dealing, so the control volume is changing after delta T time. So, that after T plus delta T, this is the position. So, this is the initial position is number 1, and this is initial second, after some time delta T, the position is number 2. So, finally, we can see that this transfer is taking place between the control volume minus 1 is this is what is the changes taking place with respect to this. So, now according to the Reynolds transport theorem, so if we consider the system, the system property, if it is B is an extensive parameter which we are dealing. So, here B system T is equal to B control volume T. So, in the previous slide, if B is the extensive property which we are dealing with, so B system at time T is equal to B control volume at time T. So, the system can be say here the system is equal to control volume plus 2 minus 1. So, here in the slide this system is control volume plus 2 minus 1, that gives the system as far as say between this as mentioned here. So, here the system is control volume plus 2 which is described in this figure, and then minus 1 as shown in that figure. So, B is the extensive parameter. So, according to the Reynolds transport theorem, so we can describe with respect to the control volume and the system like this. So, dB system by dt, the total derivative of the extensive property dB divided by dt, or dB by dt is equal to the partial derivative of the extensive property B with respect to control volume dB CV by del B CV by del T plus say the property what is the something adding to the system, or from the going to the out of the system B out minus B in, that is equal to del B by del T plus rho A2 V2 B2 minus rho A1 V1 B1. So, as we have seen here, so V1 is the velocity at this section and V2 is the velocity at this section, and so the control volume is considered here. So, now for the extensive parameter which we have described here, according to the Reynolds transport theorem, we can write say dB divided by dt with respect to system is given us with respect to the control volume del B CV by del T plus changes taking place with respect to the inflow and outflow. So, B out minus B in. So, that is with respect to time what happens, whether how much is coming to the system and how much is going out of the system. So, that is this Reynolds transport theorem. So, this finally dB system by dt can be represented as del B CV by del T plus rho A to V2 minus B2 minus rho A1 V1 B1, where rho is the density of fluid which we are considering here, and A2 is the cross sectional area at section 2, and A1 is the cross sectional area at section 1, and V2 is the velocity at section 2, V1 is the velocity at section 1. So, finally, we can write this like this in an integral form. This Reynolds transport theorem can be written like this: dB system dB by dt is equal to del by del T of say we can integrate within the control volume. So, del by del T of integral rho B dV plus on the surface what happens in the control surface integral rho B V n hat, which is the unit vector dA. So, that means finally what happens to the system is given such a way that say here say you can see that with respect to the system, say if you are considering just like a pipe like this. So, what happens to the extensive property which we are dealing is say inside the control volume. So, here you can see a control volume here. So, inside the control volume what happens and then on the surface, whether with respect to the surface means something is going inside and something is going outside from the system through the surfaces. So what happens to that surface? So that gives the Reynolds transport theorem. So the total say change with respect to time for the extensive property which we are considering here, that means dB by dt. So B is the extensive property. So the total change with respect to time, what happens to the extensive property is expressed as, say, within the control volume. Say we are considering the control volume, within the control volume what happens with respect to time as far as the fluid inside is concerned, that is given by del T of integral with respect to control volume rho B dV, and then on the surface what happens, that means what is something is coming adding to the system or something is going out of the system. So that gives the integral of over the control surface rho B V n hat dA. So that is, this is the same as the above expression. So this Reynolds transport theorem, like as described in this slide, so it gives what happens with respect to system and then the control volume inside the system. So this way we can easily represent, say, we can easily transform or we can change one system. That means if the approach is based upon the system, then we can go to get equations, or we can transform that into a control volume based upon this Reynolds transport theorem, or we can if the parameters are given with respect to control volume, we can also transform to the system. And finally, the Reynolds transport theorem, what happens with respect to the total system is, for an extensive property, what happens with respect to time is described in terms of the control volume inside the control volume, and then with respect to surface what is happening, what is something is coming through or going out of the surface. So that gives the Reynolds transport theorem. So this theorem is very useful in derivation of most of the fluid flow theories and fundamental principles, which we will be discussing later. So finally, so we can as you can see here in this slide, so dB system is, that is gives the time rate of change of an arbitrary extensive parameter of a system, say for example rate of change of mass, momentum, energy, etc. So this is what is dB by dt, and that is equal to say del by del T of integral rho B dV. So that is equal to time rate of change of the amount of B within the control volume as the fluid passes through it, plus the net flow rate of the parameter B across the entire control surface. So this slide gives say what is the Reynolds transport theorem. So the time rate of change of an arbitrary extensive parameter of a system is equal to time rate of change of the amount of B within the control volume as the fluid passes through it, plus net flow rate of the parameter B across the entire control surface. So this theorem is very useful in many of the fundamental development of the fluid flow theories and principles. So with respect to the Reynolds transport theorem, so the integral counterpart of the material derivative, as we have seen, say the Reynolds transport theorem with respect to the counterpart of the material derivative, we can write as d of dt of the particular parameter which we are dealing, that is equal to del by del T of the parameter plus V dot product del of the parameter. So this includes both the steady and unsteady effects, as we have seen. So this gives the Reynolds transport theorem with respect to the material with respect to the material derivative. So this you can see that here steady and unsteady conditions are described. So this Reynolds transport theorem we will be using many times as far as the fundamental theories development and its demonstration is concerned. So now before going to the continuity equation based upon the conservation of mass, we will initially discuss say different approaches of fluid flow behavior. So how we can analyze fluid flow behavior with respect to different approaches. So in fluid flow analysis we can have generally two types of approaches. First is called the integral approach and second one is called the differential approach. So here the fluid flow behavior is we are analyzing say with respect to either a system or with respect to a control volume. So within this we can analyze either we can go for a integral approach or we can go for a differential approach. So what is an integral approach? So in an integral approach what we are doing is we are trying to evaluate the quantities within a volume within a volume of fluid. So for example, if you consider the pipe flow here, so between this section 1 and 2 what happens, so that is what we will be discussing. So we are trying to evaluate or we are trying to quantifying within a volume of fluid. So through this we get integrated equations expressing behavior of fluid flow for control volume in the flow field. So that is what we are doing in the integral approach. So here we can have, we say in the integral approach there are basically two steps. First one is say we have to we have to check the problem or we have to verify whether the system is appropriate for a control volume analysis. So depending upon the problem, say sometimes we can go for a control volume analysis or sometimes it may not be possible. So we have to see the problem in detail whether we can go for a control volume analysis or we have to go for other types of analysis. So we have to scrutiny the problem whether system is appropriate for the control volume analysis. And the second step in the integral approach is we have to examine the behavior of the control volume. So we have to see whether the control volume is just like a fixed control volume like shown in this ball inside, it is a fixed control volume, or we have to see just like in an aeroplane it is with respect to when we are doing the analysis the aeroplane is also moving. So whether we are trying to analyze a moving control volume or we have to see whether just like we have seen a deforming or an elastic control volume. So these aspects also we have to see, we have to analyze or we have to evaluate before we choose either a integral approach or whether we are going for a differential approach. So the two essential steps before going for integral approach is we have to scrutiny the problem, we have to verify the problem whether the system is appropriate for control volume analysis, and secondly we have to see the behavior of the control volume whether it is fixed one or whether it is moving one or whether it is an elastic type of control volume. So first we have to do this two steps of analysis and then only we will be going for the integral approach or whether we will be going for other types of approach. So integral form of quantities, say we can see that most of the quantities we can describe in terms of integral form, just like say for example the volume flow rate, it is the integral of velocity over an area. So if you consider the volume of the discharge passing through, it is an integral of velocity over an area that gives the discharge or volume flow rate. And second, say for example the mass, if we consider the mass, it is the integral of density over volume. So mass, say when we are dealing with the conservation of mass, we can go for integral form of approach, and then if you consider the force, so it is the integral of stress over an area, and kinetic energy, it is the integral of v square, that means the velocity square by 2 over each mass element in a volume. So like this, say we can analyze the problem and see, say whether it is this kind of quantities, whether it is a discharge or volume flow rate, or whether it is a mass or force or energy what we are going to deal, and then we can choose the integral approach or the differential approach or other kinds of approach which we will be discussing later. So this integral approach is very useful in many problems where this kinds of say we can use it appropriately depending upon the problem. So now the second approach commonly used in fluid flow behavior analysis is called differential analysis. So in the differential analysis, what we are trying to do is we are trying to get a detailed knowledge of a flow field applied at a point or very small region. So we have already seen that most of the time we will be going for an Eulerian approach. So we will be discussing what happens in the fluid flow, what happens at a particular point or a particular section, what happens. So that is our major concern. So this differential analysis, the second kind of analysis, is very important. So what we are doing here is, as far as the flow field is concerned, we will be choosing, we will be at a particular point or a very small regions, we will be trying to see the variations or the differential of various fluid flow properties at that particular point. So in this differential analysis, we will be deriving differential equation which expresses the fluid behavior or fluid flow behavior. So differential equations are derived with respect to various theories in the differential analysis, and then we are trying to evaluate the unknown dependent variable at any space point in fluid flow for all the time. So that is what we are doing in the differential analysis. So we are trying to evaluate the unknown dependent dependent variable say with respect to space for all the time. So these two approaches, the integral approach or differential approach, both of the approaches are very commonly used in fluid flow problems or fluid mechanics problems. We will be discussing both the integral approach and the differential approach for our problems, for the development of fundamental theories in fluid flow and fluid mechanics, which we will be discussing later. So initially now we will be discussing the integral approach for the conservation of mass or the derivation of the continuity equation. So now we will discuss the conservation of mass, the continuity equation with respect to the integral form of approach. So we have seen that the just like in mechanics, in fluid mechanics also, the fundamental theories are based upon the conservation of mass, conservation of momentum, and conservation of energy. So the most of the basic principles or basic theories are developed based upon this conservation of mass, conservation of momentum, and conservation of energy. So the first we will be discussing here is conservation of mass, and the continuity equation is derived from based upon the conservation of mass. So first we will see the continuity equation with respect to the integral approach which we have seen earlier. So as I mentioned earlier here, say the mass is the integral, we can describe the mass as integral of density over volume. So we can see that here we can easily use the, when we scrutinize the problem, we can see that we can easily use the integral approach. So but anyway, as far as conservation of mass is or the continuity equation is concerned, we will be discussing also in terms of the differential approach, but first we will see the integral approach. So amount of mass in a system is, so according to the conservation of mass, amount of mass in a system is constant, or the time rate of change of mass is equal to 0. So that is the basic principles of the conservation of mass. So the conservation of mass is the amount of mass in a system is constant, or the time rate of change of system mass is equal to 0, or we can describe with respect to the total derivative dm within the system by dt is equal to 0, where t is the time, m is the mass, d indicates the total derivative. So as far as the system is concerned, say for example, if the fluid inside this ball or inside say in a container, here you can see the fluid inside this container. So we are trying to say with respect to conservation of mass, we are saying that the amount of mass inside this system, inside this say the gas inside this ball or inside this container, it is constant. So that is the basic principle. So that we can say that if there is any change of gas inside this ball or with respect to this container here, so we can say that the time rate of change of mass is equal to 0. So that is what the conservation of mass or the continuity equation says. So that we can write this the mass of the system is concerned, we can say with respect to the whether the air inside this or the water inside in a container. So the mass can be defined within the system. We can define as we can integrate with respect to the density and then the volume. So the mass of the system can be written as integral of rho dV. So now we have seen the Reynolds transport theorem earlier. So within the system, what happens, we are describing, say here, if we consider the pipe flow which we have seen. So within the system, we will be describing in terms of the control volume what happens, and then with respect to the control surface or the boundaries, say whether something is entering to the system or something is leaving from the system. So that gives the Reynolds transport theorem. So here, as far as consideration of mass is concerned, say if we apply the Reynolds transport theorem, say we can write d by dt, the total derivative of the system with respect to the mass, rho dV is equal to del by del t within the control volume which we are considering here of rho dV plus with respect to the control surface or the CS, that means exit and inlet of the system with plus the control surface, the integral or the control surface rho V n hat dA. So here this V indicates the velocity and this V indicates the volume. So now here to derive the basic equation of the continuity based upon the consideration of mass, we are using the Reynolds transport theorem. So that the d by dt of integrals with respect to system rho dV can be written as del by del t of the control volume rho dV plus control with respect to control surface integral rho V n hat dA. So this gives the Reynolds transport theorem as far as the mass which we are considering here. So now as you can see in this slide, the control volume, it can say here this is the system which we are considering and the control volume is inside what is there, and then say what changes taking place with respect to whether within the control surface, that is what we are describing. So control volume expression for the conservation of mass called the continuity equation. So now from the Reynolds transport theorem and then since according to the conservation of mass, we can write dm by dt is equal to 0. So now if we use the Reynolds transport theorem here, we can write del by del t of integral over the control volume rho dV plus integral over the control surface rho V n hat dA is equal to 0. So that means to conserve the mass, the time rate of change of mass of the contents of the control volume plus net rate of mass flow through the control surface must be equal to 0. So that gives the Reynolds transport theorem with respect to the conservation of mass. So time rate of change of the mass of the contents of control volume plus net rate of mass flow through the control surface must be equal to 0. So from this we can write, say the mass flow rate, say is equal to rho into q. So that we can express as, if V is the velocity and A is the area of cross section, so this is equal to rho into A into V, where rho is the density of the fluid. So the integral expression for the from the integral approach which we have seen, the continuity equation can be described by the Reynolds transport theorem as given this equation del by del t of over integral over the control volume rho dV plus integral over the control surface rho V n dA. So this gives the integral form of the conservation of mass or the continuity equation. And finally, if it is steady state condition, we can say that mass change can be written as rho into AV, where V is the velocity here. So finally, the continuity equation integral form, say if the system is steady at steady state, or if there is no change with respect to the density, that means there is del rho by del t, that means no change of density with respect to time, this can be written as 0. So, most of the fluid flow which we will be discussing will be there will not be any change as far as will be rho density is concerned, or we will be generally dealing with incompressible fluid flow. So, that del rho by del t is equal to 0. So, finally, if the density is constant, we can write A1 V1 is equal to A2 V2 for the system which we are considered, and if the system, if it is non-uniform, or if it is not uniform, then we can write rho 1 integral over area A1 V1 dA is equal to rho 2 integral A to V2 dA, or this for the non-uniform flow we can write rho 1 V1 bar A1 is equal to rho 2 V2 bar A2. So, this gives the integral form of the continuity equation. So, as we have seen here, we can use the general expression if you deal with compressible flow also, and in the case of incompressible flow we can write the equation, since here del rho by del t is equal to 0. So, that we can write the integral form of the continuity equation as, say, rho V1 bar A1 is equal to rho 2 V2 bar A2. So, here what it says is, say, with respect to this, if this is the system is just like in a pipe system which we are dealing. So, the fluid entering say with respect to system, that should be equal to the fluid leaving from the system. So, that say we have to use this equation here. So, the continuity equation, as we have seen here, the mass is conserved, and we have also seen that there can be a moving or deforming control volume. So, in that case, the with respect to the continuity equation or the conservation of mass, we can write dm system dt is equal to del by del t of control volume rho dv plus over the control surface rho w, instead of v here we are using rho w n hat dA is equal to 0. So, for the case of a moving or deforming control volume, this w is the relative velocity. So, since the system itself, the control volume itself is moving or deforming, so with respect to that we have to consider the changes taking place with respect to the relative velocity. So, for moving or deforming control volume we can write the continuity equation as, say, dm by dt is equal to del by del t of integral over rho dv plus over the integral over the control surface rho w, where w is the relative velocity n hat dA. So, where n hat is the unit vector. So, this gives the continuity equation in the say the integral form. So, for example, now if you consider a pipe with a branch, say like in this slide. So, here we can express the continuity equation, say like here. Say if at this section 1, if V1 is the velocity and area of cross section is A1 and the density here is rho 1, and at section here at the inlet 3, if the velocity is V3 and area of cross section is A3 and density is rho 3, and then here at this location, if the density is rho 2 and A2 is the area of cross section and V2 is the velocity. So, here you can see, as far as this system is concerned, there are two inflow at 1 and 3, and then there is an outflow at 2. So, finally, we can write rho 1 A1 V1 plus rho 3 A3 V3 is equal to rho 2 A2 V2. So, if the density is same, we can write this equation as A1 V1 plus A3 V3 is equal to A2 V2. So, this way we can write the, with respect to the integral form of the continuity equation based upon the conservation of mass, we can derive the continuity equation for various systems. So, now before discussing the differential approach for continuity equation, now we will see few example problems as far as the the continuity equation is concerned. Now, we will say a simple example initially we will see. Here the example which we are discussing here is same. Example 1 is as shown in figure, water flows steadily from a fire hose. So here there is a pipe through which a fire hose is connected. So there is a constant supply to the fire hose here, and from which we are taking through a pipe system connected with a fire hose, we are taking water through this for various purposes. So if the nozzle exit velocity must be at least 10 meter per second. So here the exit velocity is 10 meter per second. So we want to determine the minimum pumping capacity for which say here is the flow. So here this is the direction of the flow. We want to determine the minimum pumping capacity for this symbol system. So here this is the fire hose and this is the through which the flow takes place, and say if you consider the control volume, now the control volume here you can see that this gives the control volume with respect to the fire hose which we are considering. So here the velocity, the exit velocity is given as 10 meter per second, and here the diameter of the pipe, the hose is given as 20 millimeter. So we want to find the minimum pumping capacity such that the system is say the system considered is supplying a minimum of 10 meter per second. So with respect to the continuity equation which we have seen earlier, so here we have a control volume and then a control say system, that means the control volume you can see here in this figure. So this gives the control volume is here, and then with respect to the inlet, this is the control surface, that means what is going inside and then what is going outside. So there are two, one inlet and one exit for the system is concerned. So the continuity equation which we have seen earlier, we can write with respect to the integral form which we have discussed. So as del by del t of integral over the control volume rho dV plus integral over the control surface rho v n hat dA, that should be equal to 0 according to the continuity equation. So here the say the time rate we are not considering, so this term goes as 0. So since the flow is considered as steady, so that we can write the final system as over the integral over the control surface rho Vn dA. That means with respect to the system is concerned, say with respect to what is going inside to this control volume inside the fire hose, that should be going out through the exit. So what is entering, that should go through the exit. So now if you consider the second part of here of the continuity equation, so that is integral C over the control surface rho Vn dA, that can be written as m2 minus m2 dash minus m1 dash, that means what is entering that is equal to m1 what is leaving. So finally we can write rho 2 q2 is equal to rho 1 q1, that means through the system what enters that should leave through the system through the exit from the system. So rho 2 q2 is equal to rho 1 q1. So here if we assume that since here we are considering water, so rho the density is same, so that we can write q1 is equal to q2, so that is equal to v2 into a2. So here for the fire hose which we are considered, the radius is the diameter of the hose is given and the velocity is given, so that we can write finally the discharge, that means the minimum pumping capacity should be q1 is equal to q2 is equal to v2 a2. So that is equal to the velocity is 10 meter per second, 10 multiplied by the area of cross section of the pipe, that is pi by 4 d square. So d is 0.02 or 20 millimeter. So finally this is the pumping capacity for the fire hose system which we have seen in this particular figure. So here q is equal to 0.00314 meter cube per second. So this is a simple problem where we can use this integral form of the continuity equation. We will also discuss another simple example. which is related to the conservation of mass based upon the continuity equation. So, the problem here is a centrifugal pump has got a discharge capacity of 50 liters per second as shown in figure. It has an axial inlet diameter of 9 centimeter and an impeller of 20 centimeter diameter. So, it can be assumed that 10% of the outlet area is occupied by blades. So, we have to determine the axial velocity in the inlet pipe and the radial component of velocity at the outer impeller. So, this is the problem. So, here there is a flow takes place to the centrifugal pump in this direction, and here the diameter of the axial inlet is given as 9 centimeter, and here you can see that there will be in the inlet pipe there will be outlet area blades will be there with respect to the centrifugal pump. So, this way once it enters here and then it should go through this direction and this direction. So, here the diameter is given as 20 millimeter and here also 20 millimeter, and here this impeller total diameter is given as 20 centimeters. So, we want to find the axial velocity entering through the inlet pipe and also the radial component of the velocity at the outlet of the impeller. So, this is the problem which we are discussing here. So, here the discharge for the problem is given as 50 liters per second. So, the discharge can be written as Q is equal to 0.05 meter cube per second. Q is equal to the discharge is equal to 50 liter per second, or it can be written as 0.05 meter cube per second. So, at inlet, so here the inlet is here. So, at inlet we can write a discharge is equal to area of cross section multiplied by the axial velocity. So, that what is entering that should go through the impeller on both through the impeller. So, that we can write Q is equal to A into VA is equal to VR into AIR. So, A is the area of cross section of the inlet and VA is the axial velocity and VR is the radial velocity and AIR is the area which we will be considering. So, the axial velocity can be obtained as so the discharge Q is known. So, that is given as 0.05 meter cube per second. So, at inlet the area of cross section can be written as pi by 4. The diameter is 9 centimeters. So, pi by 4 into 0.09 square. So, that gives the an inlet area of cross section, and then axial velocity is equal to the axial velocity VA is equal to Q divided by AA. So, this is equal to 0.05 divided by this AA, that is 0.00636. So, that gives the axial velocity as 7.86 meter per second. So, now to find the radial velocity we can calculate the effective area with respect to since 10% of the outlet area is occupied by blades. So, we can find the effective area by taking the diameter of the impeller. So, pi that is equal to pi into 0.2 into 0.025, since 20 centimeter is the here 20 centimeter is what is given here, and then say 0.025 is the say this depth. So, pi into 0.2 into 0.025. So, this is actually 0.025, and this is 25 millimeter, not 20, it is 25 millimeter. So, pi into 0.2 into 0.025 into 90% is the effective area, since 10% is occupied by the blades. So, into 0.9, so that gives the AR. So, from that we can get the radial velocity is equal to Q by AR. So, that is equal to 3.5367 meter per second. So, like this we can use this integral approach of the continuity equation or the conservation of mass to solve various examples. So, this is the conservation of mass or the continuity equation is one of the basic equation which is used in all the fluid flow analysis, So this is the integral form. Now we will be discussing about the differential form later. So before going to the differential form of the continuity equation, here you can we will see in this slide the linear motion and deformation. So before going to that, the differential of the continuity equation, we will see with respect to fluid movement how the linear motion and deformation takes place. So here you can see that a container here, delta y is the size, delta x is this direction, and velocity in the x direction is u, velocity in y direction is v. So with respect to this, say here, say from one section to another, the velocity change is u plus del u by del x into delta x, and velocity change in the from one section to another in the y direction is v plus del v by del y into delta y. So the volumetric dilation rate, that means with respect to the volume inside the system, the dilation, that means the change or the rate of change of volume per unit volume, can be expressed by this equation, since we will be dealing with the velocities in x, y and z direction. So del v is equal to del u by del x plus del v by del y plus del w by del z. So where u, v and w are the velocity components in x, y, z direction. So the total, the rate of change of volume per unit volume is expressed as del u by del x plus del v by del y plus del w by del z. So now you can see that the volumetric dilation rate is 0 for an incompressible fluid. So when we are dealing with incompressible fluid, the volumetric dilation rate is 0. So that we can write the variation of velocity in direction of velocity is del u by del x, del v by del y and del w by del z. Since we are dealing the velocity components in x, y, z direction, so del u by del x gives the velocity x direction, its variation in x, del v by del y gives the velocity change in the direction of y, del w by del z gives the velocity change in the direction of z for w. So variation of velocity in direction of velocity simply cause the linear deformation for fluid element, or shape does not change for the linear variation. So cross derivatives such as del u by del y only cause the angular deformation. So but otherwise in the linear motion is concerned, the variation is we can the velocity in the direction of velocity simply cause a linear deformation. So shape does not change. So now the next lecture we will be discussing the deformation, and then we will be discussing the vorticity, and then further we will be going to the differential approach of the continuity equation or the conservation of mass.